Reminder, please all participants make sure the microphone in a mute mode, okay, to make sure our session in a very good condition and clearly delivered. Right, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi taala wabarakatuh. For all professors, associate professors, lecturers, and researchers, and also all participants today. Inshallah, today we will bring a webinar session series that will share a significant topic in wireless communication technologies, where we will share the topic focus on antenna. So ladies and gentlemen, this sharing session is called Stay Motivated Weekly Sharing Session with 5-star UiTM Research Group and Research Interest Group Webinar Series 4.0 2022. Actually, this program is initiative that organized by Department of Research Nexus UiTM or Renew under Office of Deputy Vice-Chancellor Research and Innovation UiTM. Yeah, and I believe this initiative objectively to ensure all lecturers and researchers in UiTM, Shah Alam, and all campuses consistently and continuously motivate to do a research, because as we know, maybe almost 2 years, right? Our research activity in UiTM is descending because of effect of COVID-19. Right, so inshallah, before we proceed to further session, please allow me to introduce a little bit what ARC is and who our guest speakers today. So, for our information, Antenna Research Center or ARC is one of the research group that actively doing the research on antenna design. And now many research activity have been conducted in designing microchip antenna, plasma antenna, and wide antenna as well. And actually, all these kind of antenna usually used for mobile wireless application, short distance wireless application, and satellite system as well. So inshallah, to talk about the topic today, we have two honorable guest speakers from ARC. They're actively doing the research in antenna technology. So our first guest speaker is IRTS Dr. Suhaila Subahir, lecturer of School of Electrical Engineering, UiTM Shah Alam, and she will talk about antenna technology in underground cable fault detection system. And our second guest speaker is IRTS Dr. Hajar Ja'afar. Actually, she is a very young lecturer and is very active also. She is a lecturer from School of Electrical Engineering, UiTM Terengganu branch, Terengganu, and will share a topic related to reconfigurable plasma antenna. Okay, so I think without further ado, I would like to invite IRTS Dr. Suhaila as our first guest speaker to deliver his sharing session. Okay, Dr. Suhaila, please, floor is yours.
Okay. I try to share my slide, inshallah. Is it have the slideshow here?
Yeah, clearly display.
Oh, clearly display the slideshow. Okay. Okay, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Why do I don't have my slide? I'm sorry. Just a minute. I'm sorry, I'm having some difficulty here. Some error here, so please give me some time. So Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Sorry for having some technical problems here. So I introduce myself as my name is I am Suhaila binti Subahir, and before I share my topic research today, I would like to introduce the Antenna Research Center, which is a research center under School of Electrical Engineering, College of Engineering. And this ARC is located at level 7, block 5. And if you all have a free time, so please come to visit us here. Okay, so this is our organizational chart or organizational structure. And this ARC start with Antenna Research Group previously, and it was led by Allah Yarham Prof. Dr. Muhammad Tarmizi Ali. And since 2019, IR Dr. Nurul Huda Abdul Rahman as a leader of this, as the head of the ARC, and myself as the deputy of the ARC. And here we have 6 researchers, and from left is the Dr. Rabiatun Adayah Awang, and we have Captain Dr. Muhammad Aziz Aris, we have Mr. Hamizan Yun, IRTS Dr. Hajar Ja'afar, Dr. Nur Hafiza Abdul Aziz, and we have from other school, which is Dr. Rahidawati Shahrudin from Chemical Engineering. And also, ARC also has the associate researchers from inside and also the outside UiTM, where we have IRTS Dr. Ahmad Azlan Abdul Aziz from Polytechnic Shah Alam, and also TS Dr. Nurul Azlina Ramli from Sagi College. And we have from Mechanical Engineering, which is Dr. Muhammad Shariman Adnan, and our development is helped also by one assistant engineer, who is Mr. Muhammad Fadili Ridwan. Okay, so our niche areas for this ARC is for the antenna applications, for the antenna design, and with the many applications, which are wearable and textile antenna. Okay, aperture antennas includes the reflector and also the dielectric lens. We have also multifunctions antenna such as plasma antenna and LED antenna, and this plasma antenna will be shared by Dr. Hajar after this. And also we do research for new antenna materials to apply for the flexible antenna, and we do the transparent and also the green biocomposite antenna, and also we have the reconfigurable and array antennas. And all our niche areas are depends to the applications, not strict for mobile, and also we do the RFID applications for the medical application and also the radar application. And since the establishment of the ARC, we have successfully developed several research products of antenna for many applications, such as the flexible antennas. This is the flexible antennas. Okay, we have designed the printed antennas, which we use microstrip, FR4, and also the NFC. And we did the wearable antennas. For these wearable antennas, we do a collaboration with textile department in FSG to develop fabrics involve the integrating conductive and also non-conductive yarns. Then we have also designed multifunction antennas such as plasma antenna and also the LED antennas, where these antennas not just give the illuminations for the users, but it also can provide the Wi-Fi signal applications. Other than that, our researchers also designed the reconfigurable antenna, where these reconfigurable antennas depends to the applications, including the frequency reconfigurable, pattern reconfigurable, or polarization reconfigurable. Okay, so we have complete facilities in developing the antenna, starting from the simulation, where we do have the license for the CST simulation tools, where this CST is the microwave studio for the microwave design. Then we can fabricate using the LPKF prototyping machines, and this machine is for producing the PCB prototypes and small batches which configured where it is very neat and useful for those working with the RF and microwave designs. So for the measurements of the antenna, we have spectrum analyzer up to 40 gigahertz, and this ARC also is equipped with the anechoic chamber room, where this is the room where measurement of radiation characteristic of feeds and millimeter wave antennas up to 18 gigahertz. And this anechoic chamber provides RF proof environment where both the antenna and also the measurement device are isolated, fully isolated from the outside interference and stray field. So we do have also the fabrication station has a wide range of tools available for use from the start to the end of the process. Okay, we have screen printer, punching machine for via fabrication, and several ovens for reflow process and general hand tools. We also have the developer and etching machine. So there is a milling machine and a lamination press which can be used to fabricate for large scale planar circuit, as well as patch antennas and also the similar device. So we can say that we have full facilities to design from scratch to the model antenna. So for the ARC also, we already organize many activities involving students, organizations from inside and also the outside of UiTM, local and also the international. And we do have collaboration with MATS, and we did several workshops, amateur radio with students, and also we received requests from the outside participants to join. And these are the achievement and recognition from our research, and we already have several gold awards from the ITEX, Pachipta, IDEX. Okay, so we are very proud to have this collaboration and this achievement. And these are the current research students. We have 14 PhD and Master Science. Actually, we have 4 Master by Research. And these are the graduated students, alumni for the IRC. And we welcome for all of you to come and collaborate with us if you have any project regarding the antenna or sensor design for your application. Okay, to the Antenna Research Center located at level 7, block 5 of College Engineering, or you can directly contact us using this number 5544 with extension 8239, or you can direct Gmail to us, and you can see our project and also any activities through the Facebook Antenna Research Center UiTM, and also the Instagram arc.uitm. Okay, so that is my introduction for the Antenna Research Center itself. So I welcome for you all to come and visit us. So I start with my sharing session, which is the title is the Antenna Technology in Underground Pilot Cable Fault Detection System. Actually, this project comes from a collaboration with the TNBR, and we did have a grant, okay, and a grant from the TNBR, and they request to have an RF sensor to pinpoint the underground pilot cable fault detection system. Okay, so for the background of the what is the pilot cable itself, okay, generally based on the records on the pilot cable routes, so the routes are not well maintained and updated, and most of the pilot cable routes are unknown, okay, because it is buried long ago. Okay, so in addition, the power distribution network also does not have any specific equipment or techniques to identify the exact location of the pilot cable fault along its route. Okay, so this is a difficulties to find a pinpoint or an exact location of that faulty cable. And this shows the pilot cable itself, where these pilot cables used for protection scheme, communication channel for tool control, and also the supervisory control and data acquisition purposes. And this pilot cable is usually laid underground next to the underground power cable. So we can see from here the cut of the power cable, pilot cable itself with several pairs of cable. And these are the joint of two cables. And currently these pilot cables, there are two types, which 12 pairs for 11 kV and also the 37 pairs for 33 kV systems. So these are all the pilot cables are buried underground. So for the time being, there is no specific equipment or techniques to identify the exact location of the pilot cable fault along the route. So the current method used to pre-locate pilot cable fault is a combination of insulation resistance, which is IR, and contact resistance, which is the contact resistance test meter, and also they do have the techniques using the time domain reflectometer, which is TDR, and this coupled with the knowledge of pilot cable route. Okay, so the IR test here is used to check the pilot cable insulation strength. So where the higher the value, so the better the insulation. And the CR, which is contact resistance test, is used to check the continuity between the pilot cable pairs. And the DCR value is dependent on the length and condition of the pilot cable. And this consistent value of CR, which is the contact resistance, for all pilot cable indicates a good connection of the pilot cable circuit. Other than this pinpoint fault meter, so the TDR also used to pre-locate or trace the potential fault locations in the pilot cable by carefully analyzing the high frequency pulse reflection. So for this TDR, they are using the high frequency pulse reflection also, but the characteristics and the pattern of high frequency pulse reflection shown in this TDR determine the type of fault, where this type of fault that it can detected by the TDR is the open circuit fault and also short to ground fault, but still they didn't get the exact location for the fault of cable. So from these problem statements, okay, we can see that the pilot cable's routes are not well maintained and updated because of most of the cable routes are unknown. And second, does not have any specific equipment to identify the exact location, and also no established technique to pinpoint the exact location of pilot cable faults. And it requires longer time and higher cost for the pilot cable repair. So since there is no established technique to pinpoint the exact location of the pilot cable faults, they use a trial and error method on sites by digging the estimated location given by the TDR. And this try and error method requires longer time and higher cost for the pilot cable repair because of multiple number of locations need to be dug before the exact location can be accurately determined. And from these problems, this will increase the cost of the excavation process. So for the objectives of this project is directly to develop an RF pinpoint detection system using the RF pulse injections and with the radiation of the electromagnetic waves, which is the radio waves. And the faults that we focus into is the open circuit and also short to the ground faults. So this diagram, this figure shows the artificial short to ground fault and also the artificial open to circuit fault. Okay. So generally, we are using the high frequency injection and the radiation of the electromagnetic waves as the main concept of this RF pinpoint detection system to find the exact location of the cable fault. Okay, so these are the principle of the RF pilot cable fault detection from the transmitter, and this is the underground pilot cable under test and through the receiver. Okay, so the frequency will be injected into the cable, into the pilot box by using a signal generator at the starting point, means at the transmitter. So this signal generator is an electronic device that generates repeating or non-repeating electronic signals. And this RF will propagate through the cable, through the underground pilot cable, until the end of the cable, which means the waves travel in a direct path from the source to the receiver. And this RF does not penetrate deeply into the electrical conductors, but tends to flow along their surfaces. The strength of the signal, which detected by the receiving antenna, will be indicated on the screen of the signal analyzer. And we can see the fault cable of the signal will be traced by using this detector, and the signal strength will be observed. So if the signal strength is maintained from the starting or from the source along the cable during the tracking, so this means that there are no faults or problem on that cable. But however, if the signal strength drops, okay, at the specific points on the cable, so it implies that there's a drag or fault like a cut of wire. So the cut points of the cable will make the signal losses, or the signal will be leakage from the cable, and this will reduce the strength of the signal. So due to this condition, we can see the signal strength is dropped and can be detected continuously until a certain distance. So these are the principle of the RF pilot cable fault detection, from the transmitter through the underground pilot cable, and we can detect by our receiving antenna, and we can see the signal drop through the signal analyzer. So for the development of the RF pinpoint, actually we used to have several experiment, okay, but the loop antenna gives the best performance among others. So for this is the simulation until the fabrication and also measurement in labs of the loop antenna, and this is called the loop antenna, which is considered in this project because it is more efficient to work with a wide range of frequency, where we do have a specific frequency, so we have to have an antenna with a wide range of frequency, and it will use less electricity. And this loop antenna's performance is entirely dependent on its construction and also placement. And this loop antenna also is lower or eliminate interference from other electromagnetic waves by only just receive the signals with particular frequency. So for this project, the overall dimensions of the loop antenna is 25 centimeter times 25 centimeters with the diameter 50 centimeters, and it is fabricated by using high grade aluminium with a diameter of 1.9 centimeter. And the surface current, so this is the surface current which we can see here, the red color of the loop antenna with the operating frequency of 5 megahertz, where the arrows, if you can see the arrows here for the red color here, it shows the flow of current along with the loop antenna. Okay, so we can see the red color is more current can flow there, and the distribution of the current is intense along the top and also the bottom parts of the loop antenna. And below here is the radiation pattern. We call it as a radiation pattern, which we measure at 5 megahertz, and this loop antenna radiates in bidirectional pattern. So to develop the system, the development of the loop antenna itself, first we have to use the CST Studio Suites as the simulation software to design the antenna. Then the performance of the antenna is verified by conducting measurement of the fabricated antenna, and measurement of the antenna is very crucial to make sure that these antennas are work in the real application. Measurement tools that have been used to make sure these development antennas are successful in the real application, carried out using the signal generator at the transmitter, signal analyzer or handheld signal analyzer for the receiver. And we also use the VNA and also the anechoic chamber room to test the radiation pattern overall. So these are the complete system of the pinpoint with the loop antenna with the amplifier, and this is the RF signal generator to give the RF signal to the pilot cable, and then we are using the handheld signal processing unit to detect the signal at the root. Okay, so this is the RF signal generator at the transmitter, which is the device that generates and produces the RF signal. And this device can produce various patterns of the RF signal at various frequency and also the amplitudes, and provides a signal source to underground pilot cable under test. And for this project, the best performance of the frequency is 5 megahertz with 30 dBm with a voltage of 20 V peak to peak output signal. And then it is the optimum voltage that we can use to as the input to the pilot cable for detection system. And then we use the loop antenna as the receiving sensor, okay, to detect and measure the injected RF signal strength emitted from the cable under test. So for this project also, we use the low noise amplifier to between the loop antenna and handheld signal processing unit to amplify the detected RF signal amplitude, okay, from the underground pilot cable fault location. Finally, we use the handheld signal processing to display and observe the amplitude of the signal strength from the receiving antenna, eventually determining the signal strength to indicate the accurate or the exact location of the underground pilot cable fault. Okay. So upon successful completion of the laboratory experiments and testings, so the developed system was put to test on the actual site condition for verifications and validation process. So we are given for sites by the industry to verify the RF pinpoint cable fault detection system, where these are the sites, PMU Kuala Selangor and PPU Tanjung Karang Kuala Selangor, from PPU Serukam to PPU Honda Highcom at Sungai Petani, PPU Modenas to PMU Bedong Highcom Gurun, and PPU TTDI Grove to PMU Sarjana Impian at Kajang. And for your information, PMU is the pencawang masuk utama, which has the voltage level of 275,132 kV, and PPU is the pencawang pembahagian utama with a voltage level of 33 and 11 kV. So first, these are the steps involved. First, the cable tracer was used to identify the cable route, and then we detect the estimated distance of fault. Then 5 megahertz frequency was injected to the pilot cable, okay, at 30 dBm with 20 volt V peak to peak output power using the frequency generator, and we scan the signal strength, Okay, we use the RF loop antenna as a receiver, okay, to scan the signal strength along the route of the pre-locate pilot cable fault location, and then we can monitor the signal strength from the handheld analyzer as the signal processing unit. So we can identify the exact location of the pilot cable fault based on the maximum signal strength along the pilot cable route. Okay, so from that result, we managed to get the fault cable for underground, and for the PMU Kuala Selangor and PPU Tanjung Karang Kuala Selangor. So the signal analyzer shows negative 58 dBm signal strength among others. So at this point, we have to apply the permit for the excavation process, okay, for the excavation process from the reset bodies, and after getting the permit, so the excavation to the exact location was done, and then this fault cable was obtained, and after that it can be repaired. So this the cable obtained from the PMU Kuala Selangor and PPU Tanjung Karang. Okay, so we can see here the cable was broken at the pinpoint location. And so this cable is called open circuit fault. And for the PPU Serukam to PPU Honda Highcom, so the signal strength given is negative 68 dBm, where we can see the cable were burnt underground, where the copper wire were totally twisted together at the pinpoint location. And then for the PPU Modernas to PMU Bedong Highcom at the Gurun, we can see the cable was broken at the pinpoint location, and this also is the open circuit fault. And for the PPU TDI Grove to PMU Sarjana Impian Kajang, we obtain negative 65 dBm signal, where after the excavation process, we can see the cable was broken at the pinpoint location. Okay, so as a conclusions, so this project has successfully developed based on the concept that we are using the RF pinpoint cable fault detection system. Okay, and directly we can detect the underground pilot cable fault location accurately. And from the actual site testing here, the system capable to detecting two types of fault, which are open circuit cable fault and also short circuit fault, which is buried pilot cable. However, from this project, actually there are many improvements that can be made, okay, including the range of distance, the depth from the ground surface, and also the sensitivity of the antenna, and how to do we want to improve in terms of the LNA circuit. So we are very happy to get this opportunity to collaborate with industry and having the real experience with the actual implementation. So for the summary of the site testing, we can see here the comparison between the pre-fault location using the TDR, time domain reflector, reflectometer. Okay, so this is the actual pinpoint fault location, which is using the RF concepts. Okay, so for the condition that we obtained from this 4 site testing, pilot cable was found to be broken. At PPU Serukam, the pilot cable armor and also the insulation were totally burned, and the copper wire were totally twisted together, and it shows the higher losses here. And at PPU Modernas, the pilot cable was also found to be broken, same as the PPU TTDI Grove to PMU Sarjana Impian. We can exact locate is the 162 meter towards the PPU TTDI Grove, where we can obtain the pilot cable was found to be broken, okay, as the previous thing. So I think we are very happy to have this industrial collaboration project because this is the real experience with the industry, and we can contribute a little to solve their problems actually. So for that, thank you very much for your attention.
Thank you, Dr. Suhaila, with a great sharing session. Before we proceed to the second speakers, I open to all floors for question to Dr. Suhaila. Dr. Suhaila, actually, I have one question about this kind of technologies. Okay. From your summary, I see one of the important point I got from your presentation is this approach almost accurate compared to the existing technique, because right now we are applying TDR. So from that summary is quite impressive because the detection pinpoint almost accurate. I think very accurate. So from your view, how the potential of this research in the future application if you compare to with the current technique?
Thank you, Dr. Aziz. So from this, I can say that the RF concepts, okay, we usually see the RF and also the RF or the frequencies related to the free space. But from this project, I can see that this is successfully proof that the RF also can pinpoint underground for the underground application. Okay, but it must be the exact. We must determine first what are the exact frequency that we want to use for that application. And as we know that generally we are using the free space for the RF frequencies. Okay, and also for this project, I think there are a lot of improvements that we can be made. Okay, instead of maybe we have to detect more depth from the surface ground. Okay, and for the time being, this project just can detect about 2.5 meters depth. Okay, and 500 meters distance from the source. Okay, if we have a longer distance, so we have uh, to change the source into the nearest to the pre-locate detection location. Okay, I think that
Thanks,
is
Dr. Suhaila. Okay. Right. If there is no other further question, so I think we invite for our second guest speakers to talk about his topic. So without further ado, pass to the floor to the Dr. Hajar, please.
Thank you to our moderator, Captain Dr. Mohd Aziz, and also our first speaker, IRTS Dr. Suhaila Subahir. And today I would like to present my slides which is entitled Reconfigurable Plasma Antenna. So is it clear, Dr. Aziz?
Clear.
All right, okay. All right, so today I would like to present my research area, one of my research area, which is titled Reconfigurable Plasma Antenna, which is the main topic is a plasma antenna. And I'd like to introduce myself. My name is Dr. Hajar Ja'afar. This is my email and my contact number. I'm from the research fellow from Antenna Research Center, ARC, School of Electrical Engineering, College of Engineering, Universiti Teknologi Mara, and I'm currently senior lecturer at Universiti Teknologi Mara, Cawangan Terengganu. Right. So my research area, beside the plasma antenna, also we cover for the underwater antenna and also for the 5G antenna material, which is for the flexible antenna, and also for the reconfigurable and Aris antenna. So for this presentation, it will cover for I will cover for the introduction. I will explain the basic concept for the plasma, the antenna designs, the result and discussions, summary from the monopole plasma antenna, and and reconfigurable plasma antenna array, and summary of reconfigurable plasma antenna, and the last but not least, the patent awards and fabrication that I got from this research. All right. So actually, what is a plasma, right? So we know that plasma is, we always refer as the hot state of matter. We know that we have a solid, we have a liquid, we have a gas, and the last is plasma. So how plasma generates? So when we add a heat or we increase the temperature, for example, so the molecules become more energetic and transform in this sequence from the solid to liquid to gas, and last is plasma. So if you refer this figure 1 here, so you can see that the change in states of matter. So from the solid, so when you increase the temperature, it will become liquid, and you add more heat, it becomes gas, and the last, plasma. Okay. So this concept we apply to the plasma antenna. What is a plasma antenna? Plasma antenna actually is a type of antenna in which the metal conducting element of conventional antenna are replaced by plasma elements. So before this, we know that for the conventional antenna, we are using a metal conducting elements, for example, copper, aluminium as our conducting element. But in a plasma antenna, we are using a plasma medium as or plasma element as our conducting element. So when a plasma is ionized, it is actually becomes a conductor and can transmit and receive radio signals. This is the basic concept for the antenna, which is it can transmit and in the same time it can receive radio signal. So for the monopole plasma antenna, I'm using for this part is using fluorescent lamp, fluorescent tube. So in this fluorescent tube, the gases that inside the fluorescent tube is the mercury, argon, fluorescent lamps, and method to generate plasma, I'm using the AC power supply, and my target operating frequency at 2.4 gigahertz. So for your information, there is many steps to generate plasma. One of them is DC. We can use DC. We can use the AC, and also laser and microwave. But in my research, I focus by using AC power supply. Right. So this is my designs. Right. So this is a fluorescent tube, and inside the fluorescent tube, it consists of plasma, which is the gases that the gas inside the tube is from the this one. We are using the gases. We are using mercury and argon. So this one is our coupling sleeve, and we have aluminum tape. We have a SMA connector. So this is the parameter that I'm used for to design my monopole plasma antenna. So this is the result and discussion. So you can see that I tried to compare the result with the monopole plasma antenna went on. So indicated for the red line here. Right, so it showed that it can operate at a 2.4 gigahertz. All right, and then when this one is for the measured, and for the blue line is a monopole plasma antenna for the simulated here. Okay, and when we off monopole plasma antenna, so you can see that there is it's less than 10 dB. Right? So this is the return loss simulated and measured reflection coefficients result for monopole plasma antenna. And this one is for the comparison between the simulated and measured radiation pattern of monopole plasma antenna during on at 2.4 gigahertz and in E-plane, which is in the field 90 degrees. Okay, so there is a three condition here. All right. So first condition, this one, the main target for the experiment, we want to prove that the radiation is come from the gas. All right. So the first condition, which is the coupling sleeve, was not covered. So you can see this one is the coupling sleeve. Okay, with aluminum wrap shielding box and fluorescent tube was switched on. So you can see that the signal strength here is negative 55 dB. This one. Right, so this one we are using apps for the Wi-Fi analyzer. And for the second conditions, you can see that which is a coupling sleeve, it was covered with aluminum wraps, shielding box, and fluorescent tube was switched on. So we on. So you can see that the signal strength is negative 56 dB. And when the coupling sleeve was covered with aluminum shielding box and fluorescent tube was switched off. So you can see that signal strength is very low, which is negative 85 dB. So we can say that the signal is transmitted by using when we on the lamp. So which is the conducting element using a plasma element. So actually, this monopole plasma antenna is already implemented. We implement in our ARC lab. Okay, so the ARC lab. So you can see here. So and there is the antenna functions. So we can summarize that monopole plasma antenna by using fluorescent tube is a self-fully designed at frequency 2.4 gigahertz and having integrated with 3G Wi-Fi router, and it was proven that for the commercial fluorescent tube can be used as a radio signal. Okay, now we go to the reconfigurable plasma antenna. After we proved that for the single monopole plasma antenna can transmit and receive the signals, so I tried to enhance my research for the reconfigurable plasma antenna, which is the target is to design a reconfigurable antenna by using plasma element with capabilities of impedance. So you can see here, I tried to design by using a fluorescent tube, all right, and with a 12 tube here, and at the center here is the monopole antenna, right? So the monopole antenna, the function of the monopole antenna, it will provide the signals. So you can see that this is my designs, and this is the parameter that I'm using for design the reconfigurable plasma antenna. Right, so at this design, my target frequency at 2.4 gigahertz. Okay, so this one is the antenna structure, all right? And this one is the prototype. And I'm using also the overall structure of reconfigurable plasma antenna array integrated with Arduino technology. All right, so we can set that at which fluorescent tube that we want to on or off. This one is the switch. Okay. But actually, the basic concept for the reconfigurable plasma antenna is for the first conditions, when the plasma frequency is lower than RF frequency, so the electromagnetic wave radiation passes through the plasma and the plasma becomes transparent. So you can see that at the center, my design, we have a monopole antenna. So monopole antenna, we rate it at frequency 2.4 gigahertz. So when we off in the certain fluorescent tube, so the radiation pass will electromagnetic wave radiation will passes through the plasma, and the plasma can become a transparent. That is for the first conditions. And for the second conditions, the plasma frequency is higher than RF, so it will trap the signal. So electromagnetic wave will be reflected, as the plasma behave as a conductor, and it can be used to radiate radio signal. So I think it's more clear if show these animations. So you can see for the white color is represent when we off. All right. So this one is the switching pattern of reconfigurable plasma antenna. So in these conditions, this one is our my monopole plasma, my monopole antenna here. This one when we off, this one when we on. Right. So you can see that. So the when we on, when we off this one, this one is become transparent, so it will pass the electromagnetic signal, electromagnetic wave here. All right. So for let's say we want to target at the beam, the angle at 0 degree or 360 degree. So we can off at the for the fluorescent tube number 10, 11, 12, 1, and 2. All right. So this condition also same. So when we on at the 10, fluorescent tube number 10, and we off number 3, so you can see that the radiation will go to at 30 degrees. Right. So in this my target, actually my scope of research here, target for 30 degrees. Right. So same situation when we off number 4, tube number 4, and we on tube number 11. So you can see that the radiation pattern will go to the 60 degree. All right. So same with until 360, which is one circle. It will go to until 360 degree. Right. So when we off element 8, fluorescent 8, so it will go 180 degrees. So for the 4, we on, we off 9, we go to 210 degrees. When we off 10, on 5, we go to 240. And this one, 270. So last is 300, and back to this one is 330, and this one is the last go to until 360. So this is table of number of sequence. So I successfully arrange the sequence until 12 sequence. So means that the activated element, which is the condition when we switch off the fluorescent tube. So you can see that when we off, I mentioned before this, when when I off the switch fluorescent at 10 element 10, 11, 12, 1, and 2, and we activated element which will be on the fluorescent tube number 3, 4, 5, 6, 7, 8, 9. So the main beam direction will go at 0 or 360 degree, and you can see that the gain is quite high, which is 13.04. So the concept is same, so which is the sequence is about 30 degree. This is for the 30 degree. So from these results, so this is the radiation patterns, which is for the red lines is represent for the measurement, and for the black color indicator for the simulation. So it's quite same. So we can say that we can accept the experiment. So from this research is already published in some journal, which is the high impact journal, for example, IEEE Transactions on the plasma science, also the radio engineering journals, and also for the conference paper. Okay, for this one is a flagship conference, which is Kapt for the oral presentations. So what I can conclude from this research, the simulated and measured data will demonstrate for the concepts of a reconfigurable plasma antenna array that full progesterone beam pattern characteristics. So the results confirm that the antenna could be steered in 12 directions, which is from the 0, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, and 330, respectively, at frequency that entire at 2.4 gigahertz. Right? So from this research is already patent, which is a patent with the title is Monopole Plasma Antenna. Okay, and awards which is from, we got a gold medal and also special award from Korea in International Conference and Exposition in Innovation of Institution of Higher Learning Pencipta in 2013 at KLCC Kuala Lumpur. And also we got a gold medals for the IPEX 2014. Another achievement, this is my publications from this research. And this is some of picture that I joined for this research. So I think that's all.
Thank you, Dr. Hajar, with a good presentation and answering session. So again, we are open to the question, answering question for all the floors today. Before we end up our session, actually we have given 1 hour, start from 10 to 11. Okay, one question from me, Dr. Hajar. I see from your slide, there are few parts on your installation, but it's I'm still trying to find out what actually the function of coupling sleeve. Okay, if I see you from your presentation, is it very important, the coupling sleeve, to create more signal?
Thank you, Dr. Aziz, for your great questions. Okay, so actually the function of the coupling sleeve, before the radiation begins, so the signal were connected to the tube with a coupler, which is we call as a coupling sleeve. So when the RF signals be applied to the coupling sleeve, the RF current will flow in the coils and generated an RF electric field. So, and in the same time, when the voltage was applied to the monopole plasma antenna, which is our antenna, an electric field was produced, and this electric field the current flow, will flow at the plasma medium. So the combinations of currents will oscillate on the surface of the metals, and this was caused by disturbing current in the interface between plasma and coupling sleeves. So on top of that, these two electric fields were emitted from the monopole plasma antenna and will propagate through the space. This is the function of the coupling sleeve.
All right, interesting. So thanks, that's all my question. All right, thanks to our two guest speakers for sharing their knowledge today. Thanks also for Department of Renew, right? And lastly, thanks for all participants. That's all for our sharing session, and have a great day. And Assalamualaikum warahmatullahi taala wabarakatuh. So please, we request all the participants fill the form have been shared in our chat. Thank you for attendance. So I think that's all. Thank you.